This time it's always working. Okay, I am Santi Roca-Fábrega from the University of Barcelona, and I will present here a model we have obtained of a Milky Way-like galaxy at redshift 0 and some first results of analyzing such a set of models. This work has been done in collaboration with Octavio Valenzuela, Pedro Colín, Jerry Krongol and Héctor Velázquez in Mexico, and Francesca Figueras in Barcelona. First of all, the code we have used basically is the version of the art code version from Colín and collaborators 2010. In this version, well, it's quite old version. As you can see, we have only the supernova thermal feedback. We have no radiative pressure and we have no photoionization. The point is that we are now running the same set of simulations with the same initial conditions using the most recent version that includes all that kinds of feedback. But well, for our main and original goal, it was not critical to have implemented this kind of feedback as you will see in the next slides. Well, first of all, why we wanted a Milky Way-like galaxy? Well, we wanted a Milky Way-like galaxy to study kinematics and dynamics of the large scale structures of this kind of galaxies at redshift 0. To do that, to obtain a Milky Way-like galaxy, what we have done is to use these zoom-in simulations. And in the dark matter only run, low resolution, what we have done is to select a halo with a mass similar to the one observed for the Milky Way, with a maximum of the velocity of rotation curve that is also inside the observational range. And what we have done is to select a halo that has no major mergers in the last gigayears, and that at redshift 0 has no massive satellite inside 3 to 4 virial radius. We also selected a halo that is in a filament or in a wall, not in voids or knots, to have an environment similar to the one of the real Milky Way. As I said, basically the main goal of our work was to obtain a Milky Way-like galaxy at redshift 0 with the large scale structures like spiral arms and bars, to try to recover the same results we obtained by using isolated box simulations, collision-less isolated box simulations that we have presented in these two papers. And also because, well, in Barcelona, I am inside the Gaia team in Barcelona, and we were very interested into having a model of a Milky Way-like galaxy to make mock observations in where to test the tools we will use to analyze the data from the Gaia satellite that will come very soon. In the next summer, we will have the first release. Okay, some general properties of our set of models. Basically, first of all, we have obtained this well-defined disk at the redshift 0. We have obtained a Milky Way-like galaxy that has this range of masses just in the lowest range of the observational values. We have also a high number of disk particles, stellar disk particles, which is something that we require for our simulation to be allowed to study these large scale structures, so the spiral arms and the bar. We need a large number of particles. In this case, we have more than 1 million particles in the disk. And our resolutions are around 100 parsecs at redshift 0, and also the temporal resolution is around 5,000 years, and the mass resolution for the stars is around 1,000 solar masses. In here, what is most interesting of this figure, I show you the rotation curve of our best model. You can see that the rotation curve of our model, which is the black one, fits quite good with the observations. The most recent observations from Reita and collaborators 2014, which is from the regions of star formation, and also with the hypothetical rotation curve obtained by HMN and collaborators, in where they used the SOFU data, but they corrected the non-circular motions of the bar and of the central region of the galaxy. And as you can see, both hypothetical model of HMN and also our body model are fitting quite good. In terms of the dark matter, in all our models, the dark matter follows this Navarro-Frenkel profile, except for the center, in where we have this cusp due to the contraction of the baryons. The concentration parameter for all our models is around 20-27, this value. The one observed for the Milky Way has a very high scatter, and we can say that this is inside this very high scatter that has the observations. And one thing that is not well fitted in our models is the star formation history. Basically, as you can see here, the star formation history of the Milky Way is the one I show you in gray, shadowed in gray. And you can see that in our model we have a star formation peak much earlier than the one for the Milky Way, and also we have a star formation rate at redshift 0, which is quite below. This is sure due to the non-implementation of the radiative pressure and the photoionization of the photons, ultraviolet photons of the young stars. In the next generation of models we are preparing, we expect to correct also this problem. Okay, what was of our interest was to generate this disk, this very well defined disk. In this case, the disk we have obtained it has a mass which is a little bit below the one observed for the Milky Way, but we have 2 million of particles. Then that allows us to study these non-large scale structures. The scale length of the disk is also inside the range for the Milky Way, and you can see here in these plots, which are 40 kiloparsecs by 40 kiloparsecs this phase on, and 40 kiloparsecs by 12 kiloparsecs this age on. You can see the different stellar populations depending on the age. The white color indicates very young stars, the blue color indicates the older stars, and you can see that stars, the scale high of the stars depends on the age, and also that all populations in our models present a flare distribution. This is something that we also want to study in the future. Another important point, it was to study the spheroidal component, not only the disk component. What we have seen when studying the spheroidal component is that we have two bar-shaped structures. A first one which is concentrated in the center, and that is generated by a secular evolution of these particles. That is basically a galactic bar here, you can see it. And also that this bar is driving the formation of a bisymmetric spiral structure. That's where we are now focusing our studies. And another component, an old component, here you can see it, is very old. And we have seen that this component, this bar-shaped structure, was generated at redshift 3 in a major merger. It's not formed by the collapse of clamps in the disk, and also is not formed by the secular evolution, but is a fossil of a major merger at redshift 3. What is quite rare, and we are also studying that, is that both bar-shaped structures are misaligned 90 degrees, and they rotate exactly at the same pattern speed. We want to study now if this kind of structures, this kind of misaligned structures, is something that is very stable or not. In terms of gas, the total gas inside the virial radius is also inside more or less the one expected for the Milky Way. What is not well fitted in our model is the distribution in cold, hot, and warm gas, something that is also can be interpreted to that we have no very good feedback recipes implemented in our models. What we can say, but is that the cold gas in this case is following perfectly very well the bar structure and also the bisymmetric spirals, and also that the hot gas and the warm gas can account for the 50 and to 80% of the missing baryons in our model. In terms of the hot gas, one of the main results we have obtained and we wanted to look for, it was the distribution of the hot gas. We wanted to put our observer like being in a solar position. That we have done that. We have put our observer at 8 kiloparsecs from the center of the model, and we made some kind of mock observations of this model. What we have obtained with that is that the hot gas distribution is highly non-homogeneous and also very clumpy. And the point to that is that it could be big problem for observers because observers, when they are trying to infer the total hot gas mass in our galaxy, they need to use the emission and the absorption of X-rays, and they can do that only if there are sources of X-rays in the background. This happens only in very few directions, and for example, the most recent works of Gupta and collaborators 2014 uses only 8 directions to infer the total hot gas mass in our galaxy. What we have done is to try to find if using so little number of observations is driving to biased results or not for the total hot gas mass in our galaxy. And what we have seen basically is that if we use the commonly used approximations that are using the observers, that are a spherical uniform approach among others, and using also the column density, we are obtaining no overestimation of the total hot gas mass of our galaxy. And if we are using another parameter that is also commonly used by observers, that is the emission measure, what we are obtaining is that we are underestimating the total hot gas mass in our galaxy. The point is that we are now looking for another observable or a combination of these two observables to recover the real hot gas mass of our galaxy. Yes, okay, thank you. If we can do that, if we can recover the total hot gas mass of our galaxy, we will be able also to use this relation. Following another works, we have found that by plotting the total hot gas mass of our set of models versus the total mass inside the virial radius of our systems, we obtain a clear correlation between them, between the hot gas mass and the total mass inside the virial radius, and then that can be a new prediction, a new constraint for the total mass inside the virial radius of our galaxy. If we can recover the total hot gas mass by another observable or a combination of the ones that are now being used, then we will be able to add another constraint to the total virial mass of our galaxy. And well, I go to my conclusions. Basically, we have seen that the hot gas is distributed non-homogeneously around the galactic halo in our models, that there is no evidence of a hot gas thick disk in our models. In the figure I showed you in where we have done the mock observations, we observed that most of the gas is basically in the polar regions above the disk, not inside the disk. We also have obtained that using the warm and hot gas coronas, we can account for the 50 to 80% of the missing baryons of the galaxy. The total hot gas mass of the galaxy cannot be well recovered by observers when using only a few directions in the sky. And also that following previous works, we have seen this correlation between the hot gas mass and the total virial mass that can be used to add a new constraint to the total mass of our galaxy. Finally, I have to say that we need these new feedback recipes to properly fit the star formation history of our galaxy and also the total cold gas mass at redshift 0 in our models. As I said, just now we are running a new set of models with the same initial conditions as the ones I presented here that with the implementation of the radiation pressure on those grains, also the photoionization, and we are now still in process implementing a new recipe for the UV background, the cosmic rays, and also the AGN feedback. And that's all. Thank you.
We have time for a couple questions.
How does the size of your bar compare to the size of the Milky Way bar, and do you think that will be adjusted if you get a correct estimate on the hot gas?
Mm-hmm. The one which is coming from the disk, the one that is generated by the secular evolution, it has 3 kiloparsecs. It's more or less. You know, we have these 2 bars in the galaxy. It's more or less like the long bar. Yes. Yeah. It's more or less at the same length. The other one, the one which is older, is much more big. Yes. But it's very under the density of the old bar is very low in the disk.
Okay, let's thank Santi again. Okay, our last but
in Barcelona. First of all, the code we have used basically is the version of the art code version from Colin and Collaborators 2010. In this version, well, it's quite old version. As you can see, we have only the supernova thermal feedback. We have no radiative pressure and we have no photoionization. The point is that we are now running the same set of simulations with null range. And what we have done is to select a halo that has no major mergers in the last gigayears, and that at redshift 0 has no massive satellite inside 3 to 4 virial radius. We also selected a halo that is in a filament or in a wall, not in voids or knots, to have an environment similar to the one of the real Milky Way. As I said, basically the main goal of our, this time it's always working. Okay, I am Santi Roca-Fábrega from the University of Barcelona, and I will present here a model we have obtained of a Milky Way-like galaxy at redshift 0 and some first results of analyzing such a set of models. This work has been done in collaboration with Octavio Valenzuela, Pedro Colín, Jerry Krongol and Héctor Velázquez in Mexico, and Francesca Figueroa. Study kinematics and dynamics of the large scale structures of this kind of galaxies at redshift 0. To do that, to obtain a Milky Way-like galaxy, what we have done is to use these zoom-in simulations, and in the dark matter only run, low resolution, what we have done is to select a halo with a mass similar to the one observed for the Milky Way, with a maximum of the velocity of rotation curve that is also inside the observation, the same initial conditions, using the most recent version that includes all that kinds of feedback. But well, for our main and original goal, it was not critical to have implemented this kind of feedback, as you will see in the next slides. Well, first of all, why we wanted a Milky Way-like galaxy? Well, we wanted a Milky Way-like galaxy to